Okay. In the last video, what we observed is that supremum can be seen as the union of cuts, right? But what is the logical guarantee? We shall deal that in this video, and also we are going to conclude our big question whether whether R has the least upper bound property or not. In the last video, what we observed is we can look that supremum of A as the union of cuts, right? There are so many cuts in a set A, set which is the subset of real number, and we just union them, and we observe that it may be equal, that is the supremum of A may be equal to the union of the cuts of A. But we need to deal a little more logically now. Okay, so let A be a non-empty subset. Of course, we want non-empty. Okay, non-empty subset of R, and assume beta as upper bound. Okay, why assuming? Because we don't know whether every set has the upper bound, every subset of R. This need not be true also. So just it is nothing but we are taking the case of a subset of R which has the upper bound. Okay, let A be the subset of R, and assume beta as the upper bound of it. All right. So now what? Let gamma be the let gamma be the union of all the alphas belongs to A. We already deal with these things, right? What is interesting here is to prove this cut. Why? In the last video we just saw that this is a number, but what is a guarantee this is a number or this is a cut? All right, this to be a set, this is definitely this is the set. All right, but this to be number, this should be cut. So for that we need to prove the property number 1, 2 and 3. All right, so in this video we are going to prove that again. Okay, so let's prove the property number 1, or let's try to investigate what happening with the property number 1 of the gamma. Okay, so what we have, gamma is equals to union of all the alphas belongs to A. And what are these alphas? These are the cuts, right? So these must be non-empty set. So union of the non-empty set is non-empty set. So clearly gamma is non-empty set, that is not equal to null set. But is gamma is the proper subset of rational numbers? Okay, what we have in this here, we have, okay, let me mark that. Okay, you see this beta, this is the upper bound of A. That means this is greater than all the alphas belongs to A. This is greater than all the alphas belongs to A. So now we have, this is our question. So for that we have this statement, right? Alpha is less than beta for all alpha belongs to A. Okay, this less than means proper subset. Now what we have now again, you can see union of all the alphas is again less than beta. This is the basic properties of the sets or basic results also. Okay, basic. This is one of the basic result. All right. So I don't tell you everything regarding this. Okay, this is also very clear. So union of all alpha. What is our union of all alphas? It is this. This is gamma, right? So we here we have it. So there we have. So this is clearly gamma is a proper subset, right? Gamma is the proper subset of beta. What is beta? Beta is an upper bound. Beta is an upper bound. What is upper bound? Upper bound is a number. What is number? Number is a cut. Therefore, beta is a cut. So coming here, since beta is one of the cut, so what we have, this beta is the proper subset of rational numbers. So from this one and this part, what we have gamma is not equals to null set as well as proper subset of rational numbers. So this is our property number 1. And proving the property number 2 is also a very easy thing. Just take now what we need for the property number 1. We need a rational number in the cut. Okay, let P be a rational number in the gamma. Why it is a subset of rational number? It is again clear from here. You see, gamma is the subset of rational number. So there is nothing much to deal with this one. So I'm directly going. Okay, let along with that, let Q be one of the rational number and Q is less than P. So to prove the second property, what we require is requirement is we have to prove that this Q also belongs to gamma. Correct? Q also belongs to gamma. Okay. We shall do this is very quick. We have P belongs to gamma. P belongs to gamma. This says that P belongs to union of alphas. Right? So this says that P belongs to some alpha. For some alpha belongs to. What is alpha? Alpha is a cut. Alpha is a cut. So what we have now? Clearly. So alpha is cut, right? So what we have now then? You just think. We have P belongs to alpha, Q belongs to a rational number and Q less than. Since alpha is cut, P belongs to alpha. This implies clearly Q belongs to alpha. This itself is a self-explanatory thing. Q belongs to alpha. So Q must belongs to union of alphas. This means Q belongs to gamma. That's it. What we have now. Therefore, if P belongs to gamma and Q is a rational number, Q less than P, then Q going to belongs to P in the gamma. So this proves the second property. Second property is also done. And again, proving the third property is also a very simple one. I will do that one also very quick. If P is an element in the gamma, so our expectation is there must be an R in the, okay, there must be an R, there must be one more element in the gamma such that our P is lesser element. Let's write like this. Okay, our P is lesser element. So this is our expectation. So if P, this is also very clear. P belongs to gamma says that P belongs to union of alphas. So this is going to be P belongs to alpha for some alpha belongs to A. Since alpha is a cut and our P belongs to alpha, this says that there exists a number inside alpha itself such that our P is less than. What is this one? This is important. What is this? What is this? This implies, this marked one implies R belongs to gamma such that obviously P is always less than R. If it is in the alpha, then it is all going to be in the gamma also. It is not a big thing. So what we have now? We have, finally we have, if P is an element, then there exists an R in the gamma such that P less than R. So third property done. So what it is saying, this is clear-cut explanation that our gamma, which is the union of all the cuts in A, is a cut. That means is a real number. Okay, now it is very again very simple. See, every alphas contributes to this union, right? So clearly our every alpha is a subset of its unions. This is true for all the alphas in the A. What is this statement says? This statement says our gamma is one of the upper bound. One of the upper bound. Fine. So this is a one of the upper bound. Say there is a delta which is less than gamma. Okay, there is one cut which is less than gamma. What it says, this says that cut is less than union of alphas. What is this? This is very important. What is this saying? there exists an alpha in A such that your delta is also a proper subset of alpha. So this is not an upper bound. This is not an upper bound. Let's write what we have. We have, if delta is a cut less than gamma, then delta is not upper bound. Not upper bound, isn't it? You look here, we took this one, okay, we took this part, delta less than gamma, and we got this one as not an upper bound. That is what we are writing here. Alright, what is the contrapositive statement of this? If delta is an upper bound, if this is an upper bound, then delta will be not greater than, or gamma may be less than or equals to delta. What is saying? If there exists an upper bound, then gamma is the least among the upper bounds. This is the least one. That means our gamma is the least upper bound. It is suprema. Okay, that's interesting. What's a little more interesting or very important one is, we took A as any subset. I just didn't mention that, I think. Okay, I not mentioned, but while taking subset of R, we have no restrictions or properties of the set. You can take any set. You can take any subset of real numbers. Okay, any subset of real numbers. Then with every subset we found a gamma, which is the supremum of it. And that supremum, we again you can see in the first and most, we proved that this right, yeah, all the three properties are satisfied. That means gamma, our gamma is a real number. Fine. So what do we have? This one, a real number. So every non-empty subset of R which has upper bounds, has suprema. And note that R is an ordered set. This means our R has least upper bound property. Least upper bound property. That's it. After doing all such kind of circus and definitions, generalizations, we finally proved our R has the least upper bound property, which was missing in the rational number set. We started from finding new numbers and then defined what is meant by order, and then we defined upper bounds, lower bounds, not just those things, supremum, infimum, and then suddenly we defined what is meant by real number, and then we showed that that real number has some order in it. So then we defined in this video what is meant by supremum. So not defined how a supremum looks like with our definition of numbers, and then we showed that with every non-empty subset of real numbers, which is an ordered set, uh, has supremum. Of course, so that set should have the upper bound, so that our least upper bound property is satisfied. So this is how to prove R as a this is how to prove the least upper bound property. And in fact, we are talking about we are still in the appendix part, and uh, I think we are in the step number 1, 2, 3. Okay, we are in the step number 3. We completed the step number 3. Okay, step number 3 in the appendix part, and also we completed one part of the theorem 1.19. In that one part is proving the least upper bound property. I don't state this theorem 1.19 till we till we complete that theorem's proof. Okay, then we will arrange the proofs, and we will write down the or we shall give the statement of the theorem. So this is going to be our approach. Like we will gather the information, and then we will process them, and then we will create a new result. Then we will give a small statement of the result. Okay, so finally we came to a situation where we can say R has the least upper bound property.